All right, in our last video, we got an introduction to this parametric stuff. But now what we want to do is try and build some parametric equations from some setups, from some explanations of what curves are going to look like, things like that. And then we also want to get some practice describing or sketching these things without just plotting it point by point. We'll do some stuff where we plot a couple of points, but we want to be clever and intuitive about how we know our curve is going to move based on the formulas and functions that we get for x and y. So that's where we're at. Let's jump into this. We're going to build some parametric equations. So first, we'll just take a look at a line. Well, really, we got two lines here, right? One of them is just connecting these 2 points, and the second line is perpendicular to the first and goes through this point. So let's just go ahead and think about this. We've got lots of options here, especially because we're not given a specific interval of time that this needs to occur at. So what we can do is just pick a starting point, and we'll define our functions x and y based on that. So my starting point is going to be 0, 0. So I'll say x is going to be 0 plus, it needs to get up to 4 eventually. So maybe I'll just say 4t. That way, at time equals 1, we get x equals 4. And we can do the same thing with y, right? Start at 0, but now our rate of change of y is going to be 7. And that's what we've got. We have lots of different options that we can do here. We could also say something like x equals 2t and y equals 3.5t. What we'll notice is that now this is going to get from 0.00 to 0.4, 7 in 2 time units, right? Because it's going to take us 2 time units to end up with x equals 4 and y equals 7. Another thing that we could do is do something like negative 8t and y equals negative 14t. Now what you'll notice is that we end up going backwards. So we've kind of switched the positive orientation of this a little bit, but it all is going to work out pretty nicely. For our second one, the main thing that we need to know is that our slope is a negative reciprocal. So we've got to find the slope from the first one. It's a rise over run. It's 7 over 4. So our slope is going to be negative 4/7 here. All right, cool. So now we can just do the same kind of thing and say like x is going to be 1, and now what we're going to notice is that it's going to change in the x direction by maybe negative 7t, and then y is going to be 3 plus 4t. Again, you could switch the signs on these and do things like 1 plus 7t and y equals 3 minus 4t. You could change these rates of change of x and y as long as the ratio between them stays the same, right? We need negative 4/7 to be the general slope, so you could scale these up or down by the same amount, and it should be fine. Hopefully that's a nice little kind of brush up start to this. And now what we have is a bit different. We have 3 functions that are going to connect points, but they're piecewise. It's all really the same function, which means we have to decide on time intervals. I think an easy choice is to just say each of these lines are going to take 1 time unit, right? So this one is going to go from 0 up to 1. And then this one is going to pick up where we left off and go up to 2. And then this one is going to pick up where we left off and go up to 3. Technically, we need to be careful about this because let's say like, well, time t equals 1 only gets included in one of these things, and then the same thing for t equals 2. We could put them in the other inequalities. It doesn't really matter. But now what we need to do is come up with these piecewise functions. So first, let's just start with the red one. Pause the video, see if you can come up with the piecewise definition of a line that passes from negative 2, 1 up to 2/5. Go ahead and see if you can do that. All right, hopefully you got something like this. You'll notice our x values are increasing by 4 units, and so are our y values. And so we have negative 2 plus 4t and 1 plus 4t. Again, if you plug in 0 for these, you'll get negative 2, 1. And if you plug in 1 for these, you get you get 2, 5. Notice again, I'm not including 1 here. I could. I'm going to not, because I'm going to make one function. Maybe I'll put it like this for now. I'll make one function at the very end, and we want only one of the pieces to be defined for each of the values of time. Now, okay, here's the tricky part for the second one. Our starting point here is going to start at t equals 1. And so we were saying these were our starting points, right? But now that's not actually going to be the case. So for this, what we're going to do is say x, I'm going to start with the rate of change first. It's going to go up by one value, so I'm going to say plus t. I need to figure out what it's got to start at. It's not going to be 2, because that would then give me this point 2 comma 5 when t is equal to 0, but I want it to give me this point 2 comma 5 when t is equal to 1. So I need, when t is equal to 1, this x value is equal to 2. Hopefully you can see that this is going to be 1 plus t. Y then similarly is going to be, we've got a rate of change of minus 7. And at t equals 1, I would like the y value to be 5. And so I need something minus 7 to be 5. It's pretty clearly that that's 12. And this is going to be for 1 less than or equal to t less than or equal to 2. Now again, we'll tinker with these inequalities in a second. All right, go ahead and do this last one. What you'll notice is that we start at t equal 2. Pause the video and see if you can get this one figured out. All right, so again, I just looked at this rate of change. We're going to go up 4 units in the x direction, and I need it, when t is equal to 2, I need this to be 3. So that means I need something plus 8 to be 3. So this is going to be negative 5 plus 4t. That'll do it. And then I also need a y value. We're going to increase by 1 y value when we go from this point to this one. And I need, when t is equal to 2, this to be negative 2. So something plus 2 equals negative 2. That's negative 4. And this is for the t values between 2 and 3. So what we can do is go ahead and define 2 piecewise functions to do this. And this is what we get. I'm literally just copying down all the formulas or equations that are defining x and y for each of these pieces and then setting up the inequalities here. So hopefully that's helpful to see. Here's another example then of this. We're going to try and build a parametric equation describing a concave down parabola with zeros at positive and negative 3. And now specifically, we're only looking at a portion of it, right? We're going to map just this section, this domain from negative 3 up to 3 to this interval of t values. All right, so let's go ahead and just draw our parabola first, just so we can see what this thing looks like. We've got an x-intercept up here at 3, and another one down here at negative 3, and it's a concave down parabola, so it looks something like that. Oh, that's not very good, but oh well, I don't really care. What I'll notice is that I can come up with a function that defines this pretty easily. This is negative x plus 3, x minus 3. Now, this is just one version of this parabola, right? I could put a coefficient up here, like maybe b, I don't know, where b is some scaling factor. I can scale this up or down, and I'll just say like, okay, b has to be positive. That way it actually is a negative facing parabola. And now what we can do is try and figure out a parametric version of this. I can write this out if you want to see it. This is negative b times x squared minus 9, or you could say this is b times 9 minus x squared, right? Now, we can worry about this without this coefficient of b on here if you want, but let's just think about what's going on here. The nice thing is I know what has to happen with my x values. Our x values have to go from negative 3 to positive 3. We're going to move this way in 4 time units. So maybe like 4 seconds or 4 minutes or 4 whatever. I have to span a total distance of 6 horizontal units. I'm going to start at negative 3, and I'm going to go 6 units in 4 time periods. That's 6 over 4 for my rate of change, or 3/2. Cool. Now I've got a function that defines x. I can go ahead and just evaluate this inside of y, and that'll give me y equals b times 9 minus this x squared. So maybe I'll say this is negative 3 plus 3/2 t squared. I can multiply all this out, and we'll see what we get. But this is my function for y. So this is 9 minus this stuff squared. Negative 3 squared is 9, and then we have negative 3 times 3 halves. That's negative 9 halves, but we multiply it by 2. So that's 9t, and then we square the last term, so that's 9/4 t squared. All right, so y, then, I'm running out of room, but this is going to be b times 9 minus 9 is 0, and then we have positive 9t, and then we have minus 9/4 t squared, where b is just whatever scaling factor we want. So this is our parametric function on this interval that defines our parabola. Not too bad, right? We can do this. All right, so let's actually just look at some parametric curves and see if we can visualize them and sketch them. We will do some sketching and some plotting, but what I want to do is I want to plot my x curve and my y curve separately, just as like basic functions. So let's draw my x curve first. I'll draw a set of axes here. We've got the negative cosine function, and we're looking between 0 and 2 pi. So I'm just looking at one period of my cosine function. It's flipped upside down. So it looks like this. This is not great, but oh well, you kind of see what's going on here, right? So this is x. Now y is going to be a little bit different than that, right? We're going to have some small differences because we're raising this to the fifth. So let me draw a set of axes for the y function. I'll move it up here. Oh no, there we go. Here's my y function. And the sine function is going to bounce back and forth between negative 1 and 1. It's going to start at 0. It's going to go up to 1, down through 0 again, and then down to negative 1, and then back up to 0. And our normal sine function looks like this, right? But this one's not going to because it's raised to the fifth power, which means stuff that's close to 0 is going to get really small. It's going to stay pretty close to 0. So it's going to look like this. This is kind of a weird function. But that's approximately what your sine of t raised to the fifth function looks like, or sine to the fifth thing looks like, where again, this is 1 and this is negative 1. Okay, so how do we actually draw this thing parametrically then? Well, we'll draw a set of axes, and we'll just notice our x values are going to start at negative 1. They're going to move up to positive 1, and then they're going to come back. So we're going to go this way. Whoops, I've got my straight line tool on. And then we're going to come back this way. And our y values are going to start, they're going to be close to 0, then they're going to go up, back down, stay close to 0, down. All right, and then we'll just notice at the halfway point here, that is when our x values make it all the way across to 1, and our y values have come back to 0 at that point. So we're going to start at negative 1, 0. And then our x value is going to move forward, and our y value is going to slowly increase. So we're going to end up looking something like this. And at this point right here, we have that our x value is 0 and our y value is at its maximum. So we're hitting this thing right here. And then we're going to notice we've got this point. That's when our x value is at its maximum. It's ready to start turning around. And our y values are leveling out to 0 here. Now our x values turn around, but our y values still stay close to 0, and then they start getting negative. And we basically repeat the picture. That's a pretty bad drawing. Let me see if I can do that a bit better. There, and then, oh, I'm having a hard time drawing this one. I want that kind of shape. All right, not perfect. Oh, well. This is what we have approximately. What we can do is check this really nicely with a graphing utility called Desmos, which probably you guys have used a little bit before. Let me pull that up. So this is what it is. Plotting things in Desmos, we normally do things like y equals 2x plus 1, and there's our linear function, right? To plot parametrically, we're going to write this as a set of coordinates where this is going to be our function x, and this is going to be our function y. Now, we have to actually define these things, right? It's giving me a little error over here. It doesn't know what the heck I'm doing. So many variables, I don't know what to do. No problem, Desmos, I got you. The x function was really minus cosine of t. and the y function was sine of t raised to the 5th power. Now, it only is drawing a little portion of this, and you'll notice down here we have an inequality. We're going to go from 0 up to 2 pi. And let's zoom in on this thing. That looks pretty close to our picture. My version was a little bit worse than that. Imagine that, me having bad sketching. But that's what this thing looks like. Cool. So that's how we can get a feel for this parametrically, by just kind of thinking about behaviors. And now here's another one that we've got. We have a very similar problem. We have x equals t minus sine of t, and y equals 1 minus cosine of t. Okay, so what is going on here? Well, what this means is that our x values are increasing, right? They're going to be marching along as t increases. But this thing is going to be like anything in between plus or minus 1. So we're going to be adding and subtracting stuff. At some spots, we won't be adding and subtracting much. So what we really kind of have is like some kind of like jittery movement with our x value, right? We're going to scoot really far forward, a little bit extra on top of t when this sine of t is giving us a plus 1 here. Really, it's a minus a negative 1. And we're going to go backwards a little bit, not as far for whatever t is, right? So we're going to be moving this way. And then our y values, we're going to be up at 1, and then we're going to start getting smaller, right, based on what cosine is. And so when cosine is at 1, our y value is going to be 0. When cosine is negative 1, this is going to go up to 2. So our y values are going to kind of bounce nicely in between 0 and 2. And our x values are going to have this kind of like jittery movement where they shoot far forward and then they slow down. And they shoot far forward and then they slow down. And we're going to do this for 3 periods of our cosine and sine function. So let's just see if we can draw this. Now, I have a bit of an advantage because I wrote the problem, so I remember a little bit about what this is supposed to look like. But we can still do this. All right, where's our starting point? When t is equal to 0, we've got 0 minus 0. Okay, so our x value is going to be 0, and our y value is 1 minus cosine of 0. That's 0. Perfect. Then what we'll notice is that as we move forward, cosine gets smaller, right? And so we're subtracting less, and so our y values are going to increase. So we're going to have something that looks like this. Our x values are going to slow down, so the increases in y are going to be nice here. And then our x values are going to shoot back up again as we decrease. So we're going to look like that, right? And now we're going to bounce back up here. Something like this, probably. Oh, no. I messed that one up, didn't I? We'll revolve that around again, and we'll revolve that around again. And then this is our maximum height of 2. And what we'll notice is that this is 2 pi. So we'll call this thing pi. This is 3 pi, 4 pi, 5 pi, and all the way out to 6 pi. And my sketch is pretty terrible, but you can notice that when this is like pi over 4, then we've got pi over 4, whatever that is. When t is... these scalings are a little bit wrong, right? Because these are the values of t that I want. So those are when t is equal to all those things, not necessarily the x values. So this is when t is equal to 2 pi, right? Because we've come around in one revolution. The x value is 2 pi minus 0, so that is 2 pi. And this one is 4 pi. And so we can go ahead and still lock those in. But what I care about then is that this x value, when t is equal to pi over 4, that x value is really going to be pi over 4 minus root 2 over 2, right? That's the part that we actually care about. And so that's somewhere over here when t is equal to pi over 4. So we can see that we kind of slow down and speed up in our x movement, and we've got this positive orientation that we have. Now, this isn't great to see, but let's again fire this into Desmos and see what happens. So we'll say something like t minus sine of t, comma, 1 minus cosine t. That's what it was, right? Oh, no. There we go. All right, and you can see this is just from t being from 0 to 1, so we'll go out to 6 pi, and we'll see what this looks like. Let's zoom out and slide it around, and hey, look at that. We've got this nice kind of bouncing along on our x-axis. So parametric curves, we can still think about. They're tricky, and it does take a little bit of intuition to figure this stuff out. But hopefully this is helpful to just kind of talk through some of this and get some of the thinking that we have. Again, hopefully that's a reasonable and helpful thing to see.